Okay, and here I am. With a brief introduction of what the technical talks are and what the technical activities of CTSoc are. So first of all, let me introduce myself. I'm Fabrizio Lamberti. I'm the VP of Technical Activities of Consumer Electronics, or now it's called a Consumer Technology Society. And within the society, there are a number of areas. A couple of years ago, CTSoc launched the technical activities area in order to core the various technical activities, the technical aspects in the field of interest of consumer electronics and consumer technology. Basically, within the technical activities areas, there are the technical committees and the future directions committees, which are grouping a number of enthusiasts, of volunteers willing to contribute in these activities. In particular, at the end of 2020, beginning of 2021, 15 technical committees have been established, and I think many of you are belonging to one or more of these technical committees. Today, we will have two speeches from the AVS, Audio Video System and Signal Processing, and from the CSH, Consumer Systems for Care and Well-being. So these are just two of our technical committees. The technical committees are these groups of people representing specific areas of consumer technology. They are reporting to a technical committee board, and the future directions committee is reporting to the VP of technical activities. Here you have some other key roles in CTSoc. Our president, Wenchun Kao, VP Conferences, Nobuo Funabiki, VP Publications, Fabrice Labo, VP Industry and Standards Activities, Rahel Abdullah. The technical committees board is including also the officers of the 15 technical committees, and the future directions committees, Professor Fabrice Labo, who, by the way, has also been elected as the next president of CTSoc. The technical committees, as I said, represent the technical activities, are the core of the technical activities, are the engine of the society, as the president is used to say. They have their own websites. You can go on the main website of CTSoc and you will find a page dedicated to the technical activities and sub-pages for each of the technical committees. Each technical committee has its own officers, a chair, a vice chair, and the secretary. These are the officers who are serving for the second term. And today, I want to thank the AVS Technical Committee, the chair, Ken Sujiyama, the vice chair, Zamu Watanabe, and the secretary, David Yu, for organizing this meeting together with the CSH Technical Committee, the chair, Alessandro Tonacci, the vice chair, Lucia Billeci, and the secretary, Stanley Glenn Bruckel. Of course, if you know someone who could be interested in serving in the technical committees, I strongly ask you to share with him or her this form, which is accessible through the main website of CTSoc. They can join our technical committees and help and be rewarded in many ways. So this is basically the size of our technical committees membership. There are approximately 850 members plus around 50 officers. We selected these members, we invited these members to join initially based on the service they provided to CTSoc, but then this number is growing thanks to advertising, thanks to invitation, thanks to you who are sharing this possibility with your colleagues and friends. So the technical committees are expected to support CTSoc activities in various areas. So the technical committees are at the basics of the conferences, our publications, our standards activities, education activities, and history. And they help CTSoc in many ways, supporting the development of new initiative, helping defining new areas of attention, creating connections with other societies. Just to provide you an example, a detailed example of how the technical committees are serving. For instance, as for conferences, the technical committees are, and the people in the technical committees are helping, reviewing, and approving the call for papers of conferences. They are supporting, contributing papers and providing reviewers. They are making publicity for paper submissions. They are participating in conferences. They are collecting nominations for colleagues who are willing to help as members of the technical program committees. They are willing to help as technical program committee chairs, workshop chair, tutorial chairs, publication chair, track chairs, session chairs, and stuff like that. They are also collecting proposals for hosting conferences or maybe for academic and industry conference speakers. So not just being only limited to conferences, these technical committees over the last 2 years have nominated people for serving in the associate editor positions of our journal, the Transaction on Consumer Electronics and Consumer Electronic Magazines. They organized special sessions and conferences and special sections in journals. They have organized workshop and conferences. They have provided speakers. They have worked in joint initiative with other IEEE organizing units like the IEEE Digital Privacy. There's something new going on with the digital reality technical community, and you will hear soon about it. We worked with other society like the Signal Processing Society, the Audio Engineering Society. We launched special interest group like on the metaverse, and all the technical committees are doing different kind of activities. And years ago, they started organizing webinars and talks. So regarding the opportunities offered to members, some advertising, one of the conferences that is going to start soon is the Gaming, Entertainment, and Media, which I think is very related to this webinar today. The website has just been launched, and I'm honored to present this conference also because it will be hosted in Turin, Italy, which is where I'm personally based. And I will also serve as general chair for this conference. So I will be really happy if you consider submitting and contributing to this conference in many ways. Here you have the link and the QR code. Soon you will also receive a call for volunteers willing to serve in several technical positions for this conference. You will receive the call today. The deadline for submitting your applications is very close. We are searching for workshop co-chairs, tutorial co-chairs, publication co-chair, industry forum co-chair, demo co-chairs, and members of the technical program committee. So if you really want to and are willing to contribute, we are looking for you and will be thrilled to welcome you in Turin. So coming to the technical talks, in today's talk, the technical talks are basically an evolution of some talks which were organized in specific technical committees over the last 2 years. And we decided as CTSoc to bring these talks together and offer not just in some technical committees, but to all our members. And in particular, we decided to have them combining different perspective, not just the perspective of one technical committee. So today, this talk will be devoted to the CSH, so the healthcare related domain, and at the same time the audio and video system and signal processing domain. And well, you see that the core technologies are related to AI in both cases. So the speakers today, I'm really honored to quickly introduce them, and then I will let them introduce themselves. Professor Yu Tsa representing the Audio Video System and Signal Processing Technical Committee. He is from the Research Center for Information Technology Innovation, Academia Sinica, Taipei, Taiwan. The title of his speech will be Wearable Devices and Machine Learning Algorithms for Augmented Oral Communication Assistance. And on the other side, Arman Zafaranki is representing the TC on Consumer Systems for Healthcare and Wellbeing. He is from the University of Pisa and the National Institute for Nuclear Physics, ENFN, from Italy. And the title of the speech will be Artificial Intelligence-Based Meter for Automatic Detection of Lung Nodules in Computer Tomography Scan. As you see, the topics are indeed complementary and they are both using AI in different ways. So I will leave the floor to Lucia. And of course, if there are other chairs from the AVS technical committee, please let me know so you can organize the meeting. I stop sharing. You can be the organizer, so please feel free to take the
okay, thank you, Fabrizio, for the introduction. Thanks for the speakers for accepting the invitation to join us today, and all, of course, to all the attendees of today's meeting. As Fabrizio said, we see that there is a good link between these two technical committees, because there are some techniques like artificial intelligence, as we see in our speech today, that are shared among the two technical committees. And I think that also speech processing as used in a AVS technical committee is very useful also in healthcare domain, and for example, for some type of disabilities where there is such some speech impairment, and so speech processing devices for augmenting oral communication can be very useful also in healthcare domain. So I think that there is a good interconnection between the two technical committee, and I hope this is one possibility of sharing the information among the two and find some possible collaborations. So I think the Professor Yu Cao will be the first speaker today. So as Fabrizio said, is a professor at the Research Center for Information Technology and Innovation in Taiwan. And his expertise is about signal processing, in particular speech processing, oral communication. So I think you can start. Thank you.
Okay, thank you very much, Lucia. Can you hear me now? Okay, yes. I'm going to share. Okay, thank you. I'm going to share my screen. All right, so can you see my slide correctly?
Yes.
Okay. All right. Okay. Thank you. It is my great pleasure to present our work. And hello, everyone. Welcome and thank you for attending my talk. And I'm Yu Cao. I'm from Research Center for Information Technology Innovation. In short, it's a CT in Academia Sinica, Taiwan. And again, the title of my talk is Wearable Devices and Machine Learning Algorithms for Augmented Oral Communication Assistance. So first, let me introduce myself. I received my bachelor and master degree from National Taiwan University, and I received my PhD degree from Georgia Institute of Technology. And then I worked in Japan for 2.5 years. And during that time, I was working on speech-to-speech translation. And currently, I'm a research fellow and professor and the deputy director in CT Academia Sinica. I established the Biomedical Acoustic Signal Processing Lab, the BioASP Lab, from 2011. I was a chair and distinguished lecturer in APISPA, and I'm currently an associate editor of IEEE Signal Processing Letters and IEEE ACM Translations on audio, speech, and language processing. My team received several awards. For example, IEEE Signal Processing Society Young Author Best Paper Award, or Gold Prize machine learning challenges for hearing aid challenge, and the first place cough diagnostic algorithm for tuberculosis dream challenges, sub-challenge number 2. And my research interests include assistive oral communications technologies. That is the main topic of today's talk, and audio coding, biomedical signal processing, and speech signal processing. Okay, so this is the outline of today's talk. First, I'm going to introduce the deep learning-based speech enhancement. I will cover basic system architecture and the key factors to speech enhancement performance. Next, I'm going to introduce assistive oral communication technologies, which consists of 2 parts. The first is assistive listening technologies. The second is assistive speaking technologies. Finally, I will summarize my talk by some concluding remarks. Let me start with system architecture. As we all know that speech plays a crucial roles in human-to-human and human-to-machine communications. There are many speech-related applications. For example, smartphones, smart helmets. This is quite popular in Taiwan, and smart speakers, and also hearing aids, headsets, and in educational settings. However, speech signals are easily distorted by background noise or reverberation or channel distortion. So the performance of these speech-related applications may drop when speech is distorted. Therefore, we need speech enhancement. And the goal of speech enhancement is to improve speech quality and speech intelligibility by converting the distorted speech to enhanced one. In 2013, the first work of a deep learning-based speech enhancement system was proposed. The idea nowadays, if we look at the system, is quite simple. There are 2 phases. During training phase, we prepare paired noisy speech signals and clean speech signals, and we apply feature actuation to get acoustic features, the noisy acoustic features, and the clean acoustic features. Then we have a speech enhancement model, which is generally a deep learning model. And then the output of the speech enhancement is the enhanced results. During training, we estimate the difference of the output and the clean reference. How can we measure the difference? Usually we use L1 norm or L2 norm. This difference, usually we also call it objective function. And based on this objective function or this difference, we update the parameters in the speech enhancement model. After several iterations, we want the output enhanced results to be as close as possible to the clean reference. During testing, we use the trend SE model to enhance the noisy speech signal to get the final enhanced speech signal. Here are some demos. So for these figures, these are spectrogram plots. The horizontal axis denotes time. The vertical axis denotes frequency. The energy, the color denotes the energy. Lighter color denotes higher energy. This is a clean speech signal. Let's listen to it.
他不小心把茶杯碰翻了。
Okay, can you hear it?
Yeah.
We can
Okay,
hear,
good.
not understand, but we can hear.
Yeah, thank you very much. Yeah, sorry, this is Mandarin. Okay. Yeah, so, but if we look at the spectrogram, we can see that they are silence parts and they are also speech structures. So you can see the spectrogram plots is the structure is clear. If we have a noise in the background, if we have a baby cry noise in the background, the sound will be like this.
他不小心把茶杯碰翻了。
So it's a little bit annoying. A male speaking, and there's a background baby cry noise. If we apply traditional speech enhancement method, the result is like this.
他不小心把茶杯碰翻了。
Not very effective. If we apply another traditional speech enhancement method, the results will be like this.
他不小心把茶杯碰翻了。
If we apply deep learning-based speech enhancement, the results will be like this.
他不小心把茶杯碰翻了。
As you can hear, maybe you cannot understand, but you can hear that the speech signals are much more clear and as compared to the noisy one and comparing to the traditional speech enhancement method. And if we look at the spectrogram plots, we can see that the enhanced output is more similar to the clean one. But if you listen clearly and more carefully, you can hear that the speech signals are somehow distorted. So we need some factors to further improve the performance. And here I list 6 further research directions that can further improve the speech enhancement systems. And our group is working on these 6 directions. First, better feature extraction method and better speech enhancement model, that is better neural network models, and better objective function. And then we can incorporate multi-model input. That is the advantage of neural network models. Neural network models can accommodate different type of input data. And we can work on model size reduction and online efficiency. And we try to improve the adaptability of the neural network model to new environments and new speakers. Number 5 and number 6 are very important for real-world applications. And in this talk, I will focus on number 3 because this is related to the topic I'm going to share in the following. So, as I mentioned earlier, traditionally we use L1 norm or L2 norm to measure the difference of this output and the clean reference. The reason we use L1 norm and L2 norm is they are easy to compute, and also they are differentiable so that it can backpropagate to update the parameters in the SE model. However, we argue L1 norm and L2 norm might not be optimal. We should consider what is the main task of the speech enhancement. For example, our main task can be improve the human-to-human communication, or our main task is to improve human-to-machine communication. If our main task is to improve human-to-human communication, we should consider to get better speech quality and speech intelligibility. And if we use L1 norm and L2 norm, we might not obtain the optimal speech quality and speech intelligibility. Similarly, if our target is to improve the automatic speech recognition performance, we should consider a better objective function so that we can get better optimal recognition results. This is our motivation. So we should consider our main task, the goal of the speech enhancement, so that we design better objective function. For human-to-human, usually we consider speech quality and speech intelligibility. If you are not working in the speech signal processing, you might not understand what is the difference of quality and intelligibility. Usually I use these 2 oracles. These 2 are ancient Chinese words. Usually we can see the meaning of ancient Chinese word by its shape. This is the shape of our ear, and this is shape of our mouth. So the word here is like 1 ear listening, 2 mouths speaking. Okay, so the word over here, this is a man, this is a big ear. So the meaning of this word is 1 man with a big ear, carefully listening. So both words are the meaning of both words are hearing, but their meaning are slightly different. Nowadays, these 2 words are wen and ting in Chinese. Okay, and there is a very famous book said that paying no attention, you hear but not understand. That is 1 ear listening, 2 mouths speaking. You hear something, but you may not understand. If you pay attention, 1 man with bigger ear, carefully listening, you can hear and understanding. So intelligibility and quality are different. And for assistive oral communication technologies, intelligibility is more important. So in 2018, our team proposed an intelligibility-based objective function. Before we derive the objective function, we first want to know how can we measure speech intelligibility. So we analyze this very popular metric, that is short-time objective intelligibility, STOI. This is popularly used to measure speech intelligibility. And we found that this metric actually is simple, linear, and differentiable. So we can directly use this STOI score as an objective function to replace the traditional L1 norm and L2 norm. These two figures are the results of the human subjective listening test. We test the intelligibility and the quality. This scores is the intelligibility. How many words can be perfectly recognized out of 100 words, for example, 70, 80, or 90. And this indicates the score, 5-point score. 1 is the lowest quality, 5 is the highest quality. The result shows that if we use the same model architecture, but using different objective functions, we can get different results. And if we consider the intelligibility to form the objective function, we can get optimal intelligibility scores and optimal quality score. There are several other works trying to improve, trying to develop advanced objective functions. I list them for your reference. For the second part, I'm going to introduce assistive oral communication technologies, which consists of assistive listening and assistive speaking technologies. For assistive listening technology, which can be further divided into two parts. The first part is diagnosis. We have proposed several works. For example, automatic otitis media with effusion detection using inner ear microphones, and the vestibular hypofunction assessment using wearable sensors. You can refer to this work. And the second part, we can use speech enhancement to improve the speech signals for assistive hearing technologies. For the second part, I'm talking about assistive speaking technologies, which can be also divided into two parts. The first part is, again, diagnosis. The second part is speech enhancement for impaired voice signal enhancement. For the first part, we have derived deep learning-based or multimodal learning pathological voice detection, and also compact deep learning models for noise-robust voice disorder classification. For the speech enhancement, we can use speech enhancement techniques to improve impaired voice signal enhancement. So due to the time limitation, I'm going to present these two examples. The first one, speech enhancement for cochlear implants. The second one is speech enhancement for impaired voice signal enhancement. Let me start with the cochlear implants. This is the cochlear implant system from the outside. So we have a speech processor. We have a transmitter coil. The speech processor will convert the speech signals to electricity, and transmitter coil will send the electricity across the skin to the inner part. This is the inner part. We have a receiver. This receiver captures the electricity and stimulates the nerves in the cochlea to generate the sounds. The design of this cochlear implant is based on this traveling wave theory. It has been confirmed that in quiet condition, the CI users can enjoy high level of speech understanding. However, in noisy condition, the speech understanding remains challenging. So we propose to use deep learning-based speech enhancement for cochlear implants. Again, this plot shows the cochlear implant speech processor. In the processor, it consists of bandpass filter, envelope detection, compression, and the pulse generation. We apply the speech enhancement module right after microphone to enhance the speech signals. Here are the results. This figure, the horizontal is the SNR, from low SNR to high SNR. The y-axis is the NCM score, the higher the better. From the results, we confirm that deep learning-based speech enhancement outperforms traditional speech enhancement method. We further conduct simulation tests. That is, we simulate the cochlear implant sounds and play the sounds to normal hearing people and ask them to conduct listening tests. The results again shows that deep learning-based speech enhancement outperforms traditional speech enhancement. Finally, we collaborate with a hospital to conduct clinical tests. We further confirm that the deep learning-based speech enhancement achieve better performance than traditional speech enhancement. Next, I'm going to introduce the speech enhancement for impaired voice signal enhancement. I'm using another word, a Chinese oracle. This is the mouse, and it was trapped inside the door. So nowadays, the word is like this. The meaning is difficult to speak. Okay. Sorry? Yeah, so the meaning is speaking disorders. Okay, so there are different types of speaking disorders, including dysarthria, apraxia, aphasia, and shattering, and so on and so forth. Our goal is to use speech enhancement to improve the quality of disordered speech signals. Our first work is to improve the speech intelligibility of surgical patients. Oral cancer is the top 5 cancer for male in Taiwan. So here are some photos. This is before surgery. This is after surgery. After surgery, some muscles have been removed, so the speech can be distorted. And this is more severe case. You can imagine that the speech can be distorted very seriously. Our first work is to use a non-native matrix factorization technique to convert the distorted speech to normal speech. The idea is quite simple. We prepare the paired basis of before surgery and after surgery. This part is after surgery. This part is before surgery. During online, we try to replace the after surgery basis with the before surgery basis. These two figures shows the before surgery and after surgery. Each basis represent a particular sound. For example, this one is the vowel sound. Before surgery, it is quite clear. Only the low frequency part has energy. But after surgery, it is very noisy. Again, this is the consonant sound. The low frequency part is empty, but it has energy in the high frequency part. But after surgery, it's noisy. So you can imagine that after surgery, the speech sounds can be very noisy. So here are some examples. These are the examples before surgery and so after surgery and after speech enhancement. This is the result after surgery. And then we apply speech enhancement to improve the sound. This is the result. So the speech intelligibility has been improved. And again, we use the STOI to measure the speech intelligibility. We confirm that the speech intelligibility can be improved. We published this work in IEEE Translation on Biomedical Engineering and also Interspeech 2019. Here is another work. We try to improve the dysarthric voice. So sorry, this is Mandarin. So let's listen to the dysarthric voice. Okay, and after we apply speech enhancement, we can get clear, more clear speech signal. However, the speaker identity has been changed, so we perform another voice conversion. Okay, so this step, we try to improve speech intelligibility. This step, we try to maintain the speaker identity. This work is our collaborations with Professor Wang and Professor Liu. And another work is speech enhancement for electro-laryngeal voice signals. This is the original one. And this is the enhanced one. Okay, we published this work in ASRU 2021. And this is a collaboration work with Professor Wang and Professor Cai. Okay, let me summarize my talk. In this talk, I have presented deep learning-based speech enhancement, and I have pointed out the 5 directions that can be further improve the speech enhancement performance. And I think the objective function is very important and is related to human knowledge, and we can design better objective functions. And I have presented 2 works about assistive oral communication technologies. One is cochlear implants, another is impaired voice signal enhancement. So if you are interested to my work, here is the QR code you can scan to get the slides of today's talk. And this is my contact information. If you want to discuss more, feel free to send me an email. And here are more information and publication list of myself. And here are some references that I used in this talk. Thank you very much for your attention.
Thank you, Professor. Very, very interesting, very, very clear. I don't know if there are some questions from the audience. You can both open your phone or write in the chat if you have any question. Well, I would like to start asking you if you have performed a real-world scenario where you integrated your algorithms in the device, for example, in the cochlear implants. It's a post-processing analysis, or you have tried to integrate the algorithm in the devices? Do you think the computation cost is sufficient to integrate and perform real-life communication using deep learning?
Yes, thank you very much. Actually, our derived algorithms can run almost real time in a cell phone. Okay, in a cell phone. However, if we want to run our proposed system on a chip, very small chip, we still need to work on it. But I think in the near future, we have a chance. I mean, because like many people are working very hard to reduce the model size and also try to make the chip more stronger. So I think in the future, we can have a chip that can run our algorithms and even more complicated algorithms. Then because actually the work I demoed is not very complicated. Nowadays there are more and more advanced and more complicated speech enhancement systems have been proposed. But I think in the future, if the chip become more powerful, we can implement our system into one chip and then integrate it into a wearable device such as CI or even other hearing aids. Thank you very much for the question. Very good question.
Thank you for your answer. I think did Donato has also a question? Please.
Yes, do you hear me?
Yes.
Yes, I hear.
Okay. Thank you very much for your talk. Very interesting. I'm working in ST Microelectronics, and we have some activities within our community of researchers and also makers that explore activities on the speech disorders, and one project is related to the position of the tongue within the mouth. And so is this project some things that could address the disorder, the speeching issues based on the position of the tongue?
Okay, so your question is the position of the tongue is helpful or to generate speech signals? Is that right?
Yes, actually, typically when we in situation where you have to learn a language or you have to issues by expressing by saying a word, the position of the tongue is very critical. And it's critical also when you have to learn a language. It's not just listening, but it's also the way we position the tongue in the to the teeth, or in which part of the tongue it's used. So we are investigating the way of teaching, helping people to improve the speeching by the positioning of the tongue. It's also some things like medical activities.
Yeah, thank you very much. I think this is a very good question. So actually, we have not explored how to, teach, someone to pronounce accurate way. But we used, we know some device. It is called a smart palette. So you can put the palette. The palette is like a plastic palette with some sensors, which can measure the position of your tongue. So if the place is correct, it will show that the position is correct. If it's not wrong, it will show how to correct it. I think, but it is a company. Okay, someone from the industry is working on that, and from my team, we are not working on this direction, but I think it's highly related. What we are working on is to use the machine learning to compute what degree of distortion caused by wrong pronunciations. For example, the place of tongue or the teeth or some other factors. And so we can measure the for example, the difference of the correct pronunciation and the incorrect pronunciation, and we give a score. And we only compute that, but we do not involve we don't have a project working on. But in the future, I think it is a very interesting topic. We will explore that if we have more bandwidth. And if you are interested, maybe we can talk more. We talk about some collaborations.
Yeah, I will make in touch, create connection within the right person within my ecosystem. Thank you very much.
All right, thank you. Thank you very much for the question.
There is another question in the chat, but I think for time issue, we need to move on to the second speaker. And maybe you can, you can write an email to a professor and ask this question. Sorry, but the seminar is supposed to end at 2. So
yes.
Thank you again, and you can introduce our second speaker, who is Arman Zafaraki. From are you here?
Yes.
Okay, nice to meet you. We are
nice to meet you too.
We are both based in Pisa, although we haven't met ourselves before.
Oh.
Yeah, from CNR in Pisa. Okay, he has a bachelor's degree in information technology and a master's degree in artificial intelligence. He works at the University of Pisa and the ENFM, and his expertise is mainly on artificial intelligence for biomedical image analysis. So, okay, you can start your presentation.
Can you see my screen?
Yeah.
Yeah, now yes. Yeah.
So, hello everyone.
Sorry, maybe you can use the presentation mode, that it's more.
I'm sorry, just a minute.
Okay, now yes.
Okay.
Perfect.
Okay. Hi everybody. I hope you're having a nice day. Thank you, Professor Chow, for this great speak. I have to convey first Professor Fantacci's apology. She couldn't attend this meeting, and on behalf of her, I would apologize for her absence. AI-based for automatic detection of lung nodules in city. In this presentation, we will discuss about lung cancer nodule detection and its problems and solutions with deep learning techniques, which can improve to be CAD to be used in clinics by experts. First, I will explain lung cancer, and then lung quant automatic system will be explained to the details. Then we'll evaluate some tests on lung quant, including different data sets, pre-processing methods, and finally ideas and roadmap, maybe for the future works, and improve the lung quant for our purposes. First of all, lung cancer, we have to know what is the lung cancer and how we can detect it. Lung cancer is a malignant tumor that originates in the cells of the lungs, typically caused by uncontrolled growth of abnormal cells. It's a serious and life-threatening condition, and that can develop in any part of the lungs, even in the border of the lungs that we will see in the next slides. One early sign of the lung cancer is the presence of pulmonary nodules. These nodules are small, round in the lung tissue, and it is very difficult to detect with eyes. Even experts with years of experience can sometimes make wrong detections and determinations. And it's better to use lung CT scans for detecting these nodules. While not all nodules are cancerous, it is one of the other problems that not all nodules are cancerous, and they can be just indicative of health issues and other health issues, and should be carefully monitored. And identifying and diagnosing these nodules in early stage is crucial for effective treatment, as lung cancer is more manageable in its initial stage. Regular screening and timely medical intervention play an important role in improving outcomes for patients at the risk of lung cancer. With the evolution of machine learning and deep learning techniques within the domain of AI, there's been noticeable shift toward the development of automated systems especially in the medical field, to help and aid the experts to determine the disease in what stage it is, and how can it be treated well. These technologies also can facilitate image interpretation for experts. And one of the critical fields that deep learning diagnosed by medical image processing. This case in point, lung quant is one of the successful automated system based on the, I'm sorry, I think something get wrong. Okay. Where was I? Yeah. Lung quant is one of the successful automated systems based on deep learning, reached significant results in lesion detection of COVID-19 cases. First, I want to give you a brief big picture about lung quant. Then we'll talk about details and results and some tests that we have done on the lung quant. And the final issue is that our aim and our goal is to use lung quant for nodule detection, but the lung quant is released for lesion detection of the COVID-19. We will reach there. Lung quant is released in 2022, first version of it, but the later in 23 new version published with some changes in algorithm structure. And the main goal of lung quant is to detect infected part of the lung by COVID-19 virus. In this way, it performs by utilizing 3 different networks with 3 different objectives. BBNet, or bounding box network, is one of the difference between first and second version of the lung quant to improve the robustness and accuracy of it. Then we have 2 units for lung lesion segmentation, and also for lung and lesion segmentation. As you may know, CT is one of the complex data type because the lesions, the tissues are very hard to detect, and sometimes it's very complex without any kind of pattern. So in this situation, it's better to eliminate unrelated part of the image and to preserve region of interest, ROI. To do so, LongQuant divide into two main sections. First section is for BBNet and first UNet, which is just dedicated for finding region of interest, which is in this case long lobes. And the second unit performs for lesion detection, which is the goal of the project. As you can see, LongQuant includes different phases. As usual, every deep learning project, we need some pre-processing steps to use data in the proper way so that we can pass them to the network, like changing size or standarding Hounsfield unit range or scale range of the image, so it can be properly processed by our network. Here we want to talk about BBNet or bounding box network. BBNet is a network based on AlexNet architecture to recognize the bounding box enclosing the longs. And as I mentioned before, BBNet introduced in second version, and it improved first objective of the LongQuant. Actually, BBNet predict coordinates of 2 points in the 3D volume of CD. With these 2 points, we can form a cube over long parts. After predicting bounding box, this part cut from original images and fed into next model that we will explain. Okay. In the next phase, first unit use the cropped and normalized CTs which is responsible for long segmentation task. This unit processes the subvolumes and outputs a binary mask that represents just the long region. The long segmentation unit is trained using a combination of CT scans with and without COVID-19 pneumonia, because we want to accurately segment the long part, even if there is COVID-19 positive or negative, doesn't matter. And also here we have two post-processing part. First is watershed transformation, which separates left and right lungs. And second is connected component for eliminating small parts, which is not matter in this part, and define boundaries between left and right lobes. Also, these parts are added in the second version of the LongQuant. In the final step, there's a lesion segmentation unit, which takes the long mask generated and the original chest images as input. Based on these regions, ROI, regions of interest, second unit segment parts of the lung that are affected by COVID-19 pneumonia. As you can see here in the image, the lesion part is completely with good accuracy segmented, and it can be helpful for experts in clinics. Also, I have to mention that both of the units are modified version of the original unit architecture that has been optimized for lung and lesion segmentation. Actually, this part, as I explained before, until this part of the LongQuant, we have some mutuality with our project, which is nodule detection. But from this part on, we have to make some changes and make some alteration so that we can use this great system for our purposes. Okay, in nodule detection, we are facing slightly different problems in compare with lesion detection. But until long segmentation, as I said, they are mutual, but last part should have modified because target section is really different as the aspect of volume, tissue size, and the location is very different because the nodules can be located in every section of the lung, and also I have to mention that in the case of nodule, we kind of facing imbalance problem, an imbalance challenge, because nodules are very small in comparison to the whole image, and these are the problems that we have to overcome with to use improved lung quant for nodule detection. Now, we evaluate lung quant performance in lung segmentation and lung and lesion segmentation with different data sets to show that its generalization and robustness for our purposes. Firstly, we used COVID-19 CT scan dataset, which contains 20 patients, with 10 of them has COVID-19 positive, and the other half is negative COVID-19. And the first objective of the lung count reached 88% with this dataset. And also for the lesion part, which is the second objective of the lung quant, it reached 94, average of 94 dice for lesion segmentation. And our second and actually our main dataset is lung nodule analyzes Luna 16. This dataset is derived from LIDC IDRI dataset with excluding CT scans with a slice thickness greater than 2.5 millimeter. And Luna 16 includes 188 patients CT in 10 subjects with ground truth, and which are annotated by 4 radiologists. Also, other than the ground truths of the lung, it has coordinates of the lungs for every CT slice, and these nodules classified target into the 3 groups of non-nodules, nodules smaller than 3 millimeter, and nodules equal or greater than 3 millimeter. From Luna 16, from now we have tested around 67 patients with different number of CT slices to illustrate accuracy range in each CT slice and each patient. Here you can see the plot box for 20 patients, and which we can say majority of results are greater than 85%, but still we can see some outlier data with dots, which as my experience, I can say it's normal when you're facing with medical images because of the different type of device, different configuration. These outliers, I can say it's most of them can't be solved. And here is sample production of lung segmentation with ground truths and original data. Also, in continuing testing on lung quants, we implement some pre-processing steps to see the effect of these pre-processing on the result of lung quant. And the first step, we use anisotropic diffusion, which is commonly used for removing noise from medical images. And second is CLAHI, which is contrast limited adaptive histogram equalization, which is good in bolding the details of the image. And in this case, we really need to this because the nodules are really hide in the details of the long tissues. And I can say CLAHE performed very well in this case, and nodule can determine with better contrast. And we will see in the next slide the effect of this pre-processing on the results. As you can see here from original CT, we got segmented part of the lung, and by applying the coordinates on original CT, we got a region of interest here. And here you can see effect of CLAHE on CT slice. Also, this is one of the hard nodules, as you can see. This is exactly located in the border of the lung. And also we employed some other step on lung quant to avoid this problem. We expand the region of interest in lung parts so that we won't miss the nodules in the borders. Also, by applying coordinate of nodule, we generate a mask for nodules, as you can see here, on the long CD, which can help us for later steps. For the future work, we need more complex and more advanced networks, as our goal part of the CT is really hard to detect. And as you know, in recent years, attention mechanism alongside with different deep learning networks accomplished great results. And also attention mechanism can help the model focus on specific regions of the image that are more relevant to the segmentation task. And according to the latest review, it still can be a good field to be utilized in long CTs. Also, complex and advanced version of units like unit attention unit or unit plus can be improved the long quant performance in the first phase. Also, in the second step, which is nodule detection and segmentation in our project, vision transformer is very hot area nowadays, and most of the papers declare that there's a gap and lack of it in the medical image processing. Also, unit and unit transformer, which is published in 2022 for medical image segmentation, can be very useful for our purposes and for future works in the case of trying to produce a CAD or automatic system to help and aid experts in the real life. Thank you for your attention.
Thank you, Arman, for your nice presentation. Okay, also in this case, I ask you if you have any questions from the audience. Okay, I have a question also in this case. I'd like to ask you if you have implementing some strategies for increasing the interpretability or explainability of the network, because you know, deep learning is very powerful, but often lacks of interpretability, which can be very important in the healthcare domain. So do you think about some explainability strategies?
Yeah. Actually, our team, part of our team is working on about the explainability of AI, and we'll really like to make it more vivid that what's wrong with the network. As you know, in medical images, it's really complex data, and sometimes it's hard to say what's wrong and what we should do in the next phase. And because of that, yes, our team, part of our team is working on explainable AI.
Thank you. Any other questions or final comments? Fabrizio, do you want to make some conclusions?
Oh, well, I just want to thank again you, Lucia, for taking the floor and moderating this talk, and of course Professor Zhao and Dr. Zafranchi Zafranchi for their talks. I think there will be other opportunities. We will share these recordings, so there will be other opportunities for our members to comment on that. So thanks again, and hope there will be chances also to collaborate. I have seen that several interesting discussions started during the question and answer. So thanks again. Enjoy your night and afternoon. Thanks again.
Thank
See you in the next.
Bye. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you.